In this lecture, we will learn Boolean algebra. So as we know, in the digital signals, we are having two discrete values. So we assume that there are two values, 0 or 1. A number system based on these two digits digits known as a binary number system. In the 19th century, an English mathematician, George Boolean, developed some rules of the manipulation of the binary numbers, which is known as a Boolean algebra. So let's understand some Boolean algebraic equations. So here the Boolean algebraic theorems. So here in this theorem, so there are so many theorems available. So A plus B. So what is the theorem first? So what A plus 0. So if we add anything with the 0, then there will be no change. So A plus 0 is equals to A dot 1. So if we are multiplying A with the A input with the 1, then we are getting output as 1. And A plus, so this is the second theorem. The third theorem is A plus 1 is equals to 1. Then A dot 0 is equals to 0. So if you are multiplying anything with 0, then we are getting 0. So A plus A, then we'll get A. A dot A, we are getting output as A. So A plus inverse of A is equals to 1. Okay, so here this is a very important theorem. So we will use whenever we required for the solving some algebraic equations. A dot A bar is equals to 0. Okay, so the next equation is A dot B plus C. So this is equals to, if we multiply A plus, so A inside, so AB plus AC. Then A plus BC. Okay, so we will distribute this equation like this: A plus B in the multiplication, multiply with the A plus C. So this is the next equation: A plus AB is equals to A. So here we will see how we can prove these equations in the next slides. So A in the bracket A plus B is equals to A. Okay, A plus A bar B is equals to A plus B. Okay, so these are the few equations, more equations. As we can say, there are these are the equations. Almost 22 equations are there in the Boolean algebra. So important equations are divided into the different forms. Okay, so so this is a cumulative law. A dot B is equals to A B dot A. There is no need of a sequence. The output remains same. A dot B is equals to B dot A. A plus B is equals to B plus A. So this is a commutative law. Then associative law, A dot B dot C is equals to A dot B dot C in the bracket B dot C. And here again, sequence for AND operation and OR operation we can change. And AND law as your multiplication law. A dot 0, you are multiplying anything with 0, output is 0. You are multiplying with 1, then output remains same. A dot A dot A bar is equal to 0, as we have seen. And then this is a AND law. This is a OR law. OR law, A plus 0, A or 0 is equal to A plus 1, 1. A plus A, and A plus A bar is equals to 1. So this is OR law. Distributive law. So distributive law, A dot. So this is associative law and distributive law. Then inversion law, A double inversion equals to A. Then all other important laws are A plus A, B plus C is equal to A plus B in the bracket A plus C. A bar plus AB is equal to A bar plus B, because A plus A bar we can reduce. Then here again A bar plus AB is equal to A plus AB is equals to A plus A bar B is equals to A plus B. So these are the important algebraic laws. Now we will see how we can prove these laws. Okay, so basic operation and, or, and not. So A dot B, so 0001 and operation, or operation, and not operation. So here we have written three basic gates: truth table, and gate, or gate, and not gate. Okay, so in closure, so the closure shows that result of any operation and, or, and, oblique, or not is either 0 or 1, because we are using a binary numbers. Okay, so we are having only two values, 0 or 1. Then identifying the elements, so 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 1 is 1, 1 plus 0. So here both the operations, okay, 0 plus 1 or 1 plus 0, we are getting the output as 1. And 1 plus 1 multiplied by 1 is equals to output is 1. 1 multiplied by 0 or anything multiplied by 0 is output is 0. So 1 multiplied by 0 or 0 multiplied by 1 is equals to 0. Okay, now the commutative law. So as we know the commutative law, so let's understand how we can prove these law by using equations. Let's understand. So here the commutative law. So the two inputs, as we have learned, associative law, commutative law, associative law, distributive law, inversion law, and for law. So we will see, we can prove these laws by using truth table or the values. So A dot B is equals to B dot A, and A plus B is equals to B plus A. So let's understand how we can prove this law. So here A dot B is equals to B dot A. We are going to prove by using this truth table. So these are the values A, B. So A dot B. So A 0 dot 0 0, 0 dot 1 0, 1 dot 0 0 0. As we are multiplying anything by 0, we are getting output as 0. So here the three inputs at 0, and here if you multiply 1 by 1, then output is 1. So the A dot B's values, and same we are getting for B dot A. Okay, so here again, if I multiply 0 by 0, we are getting output as 0. 1 by 0, 0. Then 0 multiplied by 1, then output is 0. And 1 multiplied by 1, output is 1. So we can prove that A dot B is equal to B dot A. So the first law is proved. Then second law, second cumulative law, A plus B is equals to B plus A. So A plus B, now we are adding these two inputs. So 0 plus 0, 0, 0 plus 1, 1, 1 plus 0, 1, and 1 plus 1, 1. So we are getting values as 0, 1, 1, 1. And if I multiply B plus A, then again I am getting the same value. So we can, with the truth table, we can say that cumulative commutation law is proved. Now the next law is distributive law. So we can again the same method, distributive law also we can prove. So here A dot in the bracket B plus C is equals to A dot B plus A dot C. So this is a distributive law. So let's understand here A, B, C, three inputs are there. So as we know, the three inputs variation 0 0 0 0 1 0 0 1 up to the 1 1 1. So these three inputs. So A, B plus C. So these are the value A dot B plus C. So let's understand. So here B plus C, 0 plus 0 0, 0 plus 1 1, 1 plus 0 1, 1 plus 1 1, 0 plus 0 0, 0 plus 1 1, 1 plus 0 1, and 1 plus 1 1. So this is a B plus C. Now we are multiplying B plus C with the A. Now here you can see that there are 4 times zeros are there in the value of A input. So obviously all these 4 values, first 4 values become 0. So these are all values becomes 0. Then here as we know here B plus C value is 0. So again here 0 multiplied by 1, then I am getting the value as 0. And only 3 times when A's value is 1 and B plus C value is also 1, we are getting output as 1. So this is the output for A dot B plus C. Now let's understand, is this value is equal to A dot B plus A dot C. So let's understand A dot B. So A dot B, as we know, 4 times zeros are there. So this is the 4 times value will be 0. Now here the B value is 0. So here again 0 multiplied by 1. The output is 0. And here again this B plus C value is 0. So 0 multiplied by 1 is 0. And here 2 times these values are 1 1. So here I am getting 1 1 output. Okay. So A dot B. Okay, so here these why the A dot B's values are 0, because here A value is 0 4 times, then B value is 0 2 times. So 4 plus 2 6 times 0, one of the input is 0, and then only 2 times both inputs are 1. So here I am getting 1 2 times. Now let's understand B plus C. Again, same thing. 4 times zeros are there at the A input. So all these first 4 values are 0. First 4 values. Then here 2 times C is 0. So here again 0 value. Here again 0 value. And here A input is 1. C input is 1. A input is 1. C input is 1. So here 2 times only we are getting 1 input. So let's understand by adding these two values. So 0 plus 0, 0. So all zeros, first 5 times. And here one of the input is 1. So 0 plus 1, 1. 1 plus 0, 1. 1 plus 1, 1. So as we compare the A dot B plus C values and AB plus AC values, then we can say that we can prove the distributive law by using this truth table. Okay, so in this way we can prove inversion law, associative law. Same method you have to follow. Okay, same method you have to follow. You have to write the ABC value, then B dot C value, then multiply A with BC value, then find out the AB and A dot B dot C value. Okay, so let's understand that key we can prove the associative law and all the law which are there, important laws, and law, or law, associative law, distributive law, inversion law, by using truth table. Now, basic theorems and few properties of algebraic Boolean algebra. So first property is duality. Okay, so let's understand what is a duality theorem. So according to the duality theorem, the following conversion is possible. The Boolean expression. So change each AND operation to an OR operation and change each OR operation to the AND operation. So complement any 1 or 0 appearing in the expression. So duality theorem is useful for creating new expressions from the given expression. Okay, so this is a duality theorem. So let's understand AND law. As we know, basic AND law. AND law, A dot 0, AND is the multiplication operation basically. So here if we multiply any input by 0, then you'll get the output as 0. If we multiply any input by 1, then there will be no change in the output. And if we are multiplying two same inputs, then you are getting same output. And if we are multiplying A with this not or inversion, then you will get output as 0. Okay, so this we can prove by gates also. If we provide two inputs as zeros, then output will be 0. If we multiply any one input is 0, so here is the case where A is 1 and B is 0, output is 0. Then here A is 0, B is 1, output is 0. Okay, then now we can say that if we multiply A input with any of the other input is 0, then output will be definitely 0. Okay, so here that is proved. Now here, if we multiply a by 1, then output is 1. So here b is 1, and here both the cases a is equals to b is equals to 1, and here a is equals to 0, a is equals to 1. So b is equals to 1, then 0 dot 1 is equals to 0. So if one input is 1, then output remains the same as input. Okay, so here also if one input is 1, other input is 1. Okay, so same way, one input is 1. Okay, so one input is 1, other input, so the output is equals to other input. Okay, so here we said b is equals to 1, so here a is equals to 0 and here a equals to 1. So y is equals to 8 dot 1 dot 1 is equals to 1, so y is equals to a. Okay, so in this way we can prove the AND law. Same way the remaining two equation that we can prove. Then OR law, okay, OR law we can prove with the equations. A plus 0 is a plus 1 is 1, a plus a is equals to a plus a bar is equals to 1. So first law, y is equals to a. Okay, one input is 0. Okay, y plus 0 is equals to a. So if we set one input as 0 and other, if we change other input from 0 to 1. So here we are setting value of one input, that is b. Okay, here both the time b is equals to 0, b is equals to 0. And now we are changing the value of a from one time a is equals to 0 and another time a is equals to 1. So here we can say that y is equals to 0 plus 0, output is 0. Okay, so that it is proved that it is equals to a plus 0 is equals to a. And in the second time, if we one input is 0, output is equal to another input. Okay, 1 plus 0 is equals to 1. So again, but for the both the variation, we are getting the same output. Okay, so first law is proof. So according same way, for according to the first law, we can prove the other laws. Okay, other or laws. Okay, so in the first law, a plus 0 is equals to a, and if in the second law, a plus 1. Okay, a plus 1. Agar if we add for a gate, if we add 1 into the output. Okay, 1 into the output. One input is output. One input of the gate is 1. Now what indicates it? What it shows that if irrespective of other input, we will get the output as 1. And it is also proved from the truth table, because if both input or one of the input of the OR gate is 1, then definitely we are getting output as 1. So let's understand. So here in this case, b is equals to 1 for both the time, and we are changing the value from of a. Okay, first time a is equals to 0, second time a is equals to 1. So y is equals to 0 plus 1, output is 1, and y is equals to 1 plus 1, output is 1. So we can prove the second law also, a plus 1 equals to n. The third AND law is a plus a is equals to a. Okay, so we both the input. Now see here, both inputs are same. So if we connect both the input to the single input, that is a. Okay, so here a is equals to y is equals to 0 plus 0, so output is 0. And if we connect both the input to 1, then y is equals to 1 plus 1, output is 1. So again, it is proved that if the both inputs of OR gate are same, then output is same as input. Okay, so a plus a is equals to a, and a plus a bar is equals to 1. Okay, so a plus a bar. Now here see, if for the OR gate, if we use one input as a gate value and another is not or the complement of this input, then we are getting output as 1. Okay, so here a is equals to 0, and here we are complementing that, we are getting a bar. So a plus a bar is equals to 0 plus 1 is equals to 1. And again we are here, we are getting output as 1. So here again a is equals to 1 and complement is 0. So 1 plus 0 is 1. So in this way we can prove the OR law. Okay, so the inversion law, again, inversion law, the not operation is used by the by this law. Double inversion of a variable, okay, results in the original value. Okay, so if we double inversion we are using, then we are getting the original value. So here a inversion, if we provide a is equals to 0, and here an inversion of a is equals to 1, and again, if we invert this value, again we're using one more NOT gate. Then y is equals to a double inversion is equals to 0. So we are getting original value. And if we check for 1, then a is equals to 1, a bar is equals to 0. Again, we are inverting, then we are getting the same value. Okay, so this is all about inversion law, distributive law, and commutative law. Then we'll see the important theorem, two important theorem in the next lecture, that is De Morgan's theorem.